Okay, it's time for a further discussion to elaborate on the intermolecular forces from Chem Activity 27, not all of which was completed in class. Many of you worked on this in class, but I want to make sure to emphasize some of the key aspects of this for you. Intermolecular forces will also be discussed in the laboratory exercise with the water kits this week in lab. The types of bonds known to happen within molecules are intramolecular. The ones between molecules are intermolecular forces. And a hydrogen bond is one of the ones that people talk about often. The ones that have the OH or NH in them are the ones that are called hydrogen bonds. And it's a particularly strong attraction between the bonded hydrogen atom and a lone pair on another atom. The hydrogen has to be on either oxygen, nitrogen, or fluorine. So keep that in mind. Hydrogen with oxygen, hydrogen with nitrogen, or hydrogen with fluorine. There's only one molecule that has that, and so there's only one there. We're getting back to this discussion a little bit below. So the intermolecular forces that hold molecules to each other are much weaker than bonds that hold molecules together. It takes a lot more energy to break a mole of hydrogen-oxygen bonds in water molecules, and a lot less than that to separate water molecules in liquid to make them into a gas. The three types are to be noted here accordingly. Hydrogen bonding, the interaction between hydrogen attached to either fluorine, oxygen, or nitrogen on one molecule and a lone pair of electrons on a similar fluorine, oxygen, or nitrogen on another molecule. This one is our favorite one to refer to. It's the one that wins out when you have anything else to consider. It doesn't matter because hydrogen bonding is the strongest. The second intermolecular force is called dipole-dipole forces, and it has to do with polar covalent bonds. You have to be able to put a partial plus on one end of a bond and a partial minus on another end of a bond, and then you can, if it doesn't cancel out because of geometry, then you have to have then you can result in polar molecules that have a positive end and a negative end. If they don't have positive and negative ends, then the molecule tends to cancel out, and so then they're no longer polar. But if you have a positive end and a negative end, the positively polarized ends of one molecule will attract negatively polarized ends of other molecules. We call that dipole-dipole forces. London dispersion forces are possible in any molecule. At any instant, any molecule that has electrons, anything with electrons will have this type of force where some electrons are nearer to one end of the molecule or the other, and when they're nearer to one end, they tend to repel electrons in a nearby molecule or causing a partial positive charge and creating a momentary, fleeting, very short-lived attraction. It is the weakest force, but it is present in anything. So it's present in all molecules. The larger the molecule, the more you have. So these are good to know. If you didn't get it in class time today, I want to make sure you realize the difference between intra and intermolecular forces. Intramolecular forces are within one molecule, and intermolecular forces are between two molecules. So you have them when there's more than one molecule. Some attraction between them is described as intermolecular. Two or more molecules will have intermolecular forces. The other analogy that I like to use to this to help people remember what's the difference between them is if you think about interstate highways, like Interstate 29 goes through Grand Forks. Interstates go between two states when it's inter, and intra is like within something. Intramural sports are within the same school. So intramolecular is within one molecule, intramural is within a school. Intermolecular is between two molecules. All right, now the other parts of this one. We were supposed to rank the intermolecular forces in terms of their typical relative strengths. So number one is the strongest, is the hydrogen bond, and number two is the dipole. That's the second most in strength, and the London forces are the weakest. and they depend on how many atoms you are in a molecule, but in a general sense, this is the pattern. In terms of intermolecular forces, what is the trend that we described in question 13? Well, in question 13, the more polar the molecule, the more the intermolecular forces. And so there's more polarity. When there's more polarity, the intermolecular forces are stronger. And so that fits with the descriptions in the other questions as well. So it tends, the more polarity, the greater the intermolecular forces. I'm abbreviating intermolecular here, in case you didn't tell. Now, suppose we consider anything about over 1 gram per 100 milliliters in water to be soluble. And if you look at Model 2, the heaviest alcohol that is water soluble, flip over to that page, I hope you all found it, the heaviest alcohol that has at least 2 grams, or sorry, at least 1 gram per 100 milliliters soluble. The heaviest one, or the heaviest molecular weight there, is the pentanol. And then how many carbons are in that compound? Well, the name is actually suggestive of this. If you had noticed it, you can count them up otherwise. And PENT suggests exactly how many carbons that is, which is 5. And then the heaviest amine in Model 2 that's water soluble, that's at least 1 gram per 100 milliliters, turns out to be hexylamine. And hexylamine, as you might guess by its name, is going to be having 6 carbons. That's the name suggested there. If any of you end up going on to more chemistry, such as Chem 116, in organic chemistry you learn about these kinds of names. You don't have to know the details here, you can just read them from the model. Now, based on those answers, the presence of one polar functional group, namely the alcohol or the amine, apparently is sufficient to dissolve molecules to allow them to be soluble, containing approximately how many non-polar carbons. In other words, you've got 5 carbons and some polar group that goes with it. So apparently 5 or 6 carbons can be dissolved by having one polar group in with it. So let's use that in another example on the next page. There's some selected molecules of another group called ketones. You don't have to know what they are. Please note that this table is a little bit funny if you didn't notice it right away. There's a left half and a right half because there's 5 different compounds and 3 columns for each. So considering the solubilities of the ketones shown here, are they consistent with our answer to question 21? So do we have solubility for the same numbers of carbons? Well, acetone, if you look at it, has 1, 2, 3 carbons, and it's very soluble. That symbol there means infinite soluble. And so I'll make a note, 3 carbons, very soluble. Butanone, in this case, has 1, 2, 3, 4 carbons, and that's certainly got more than 1 gram per 100 milliliters, so that's good and soluble. Pentanone, 1, 2, 3, 4, 5 carbons there, and that's certainly more than 1 gram per 100 milliliters. Keep going. The next one being hexanone. If you can look at the structure here, we have 1, 2, 3, 4, 5, and 6. So that's 6 carbons, and again the HEX prefix reflects that idea. There's 6 carbons, and again we're still more than 1 gram per 100 milliliters. When you get to the next one, 1, 2, 3, 2 plus 4 is 6, and that makes 7 carbons. Whoops, 7, my tool didn't like me. Will be not as much as soluble as the other ones. So again, if you have one polar group, in this case the C double bond O is the polar group, is sufficient to dissolve the rest of those carbons to make it water soluble, as long as you only have 5 or 6 carbons. So restating that again, one polar group is sufficient to allow a compound with 5 or 6 carbons to dissolve in water. And the polar group here is the C double bond O, where you can put a partial minus charge on the oxygen and a partial plus charge on its connected corresponding carbon. So that's a polar bond, and I'll redraw it here. C with double bond to oxygen, has a very polar bond, good one to recognize for future reference, and it's going to have a partial plus on that carbon, a partial minus on the oxygen every time when you have that kind of arrangement. Okay, so looking at these examples of molecules, which ones are polar? Well, which ones have polar things have to have electronegative atoms? And so the ones that are polar are not the alkane, but the alcohol, because it has an OH group in it, that's polar. The alcohol is polar. The ether is not quite polar because it doesn't have a plus and a minus. It's got electronegativity, but it's not really polar. The amine has an NH group in there, so it's polar. That is a polar bond. We saw that those are the ones with the strongest intermolecular attractions on the previous page. And then the ketone, oh, look at that again. Well, here we have the partial minus, partial plus in that carbon double bonded to oxygen, and that makes for another polar molecule. Oops, I wrote the letters wrong. Ketone. All right. Now, which of those molecules can form hydrogen bonds to other molecules that are identical to them? They have to have either OH or NH. So make sure you look for those things. And only the ones that have those features will be able to do that kind of hydrogen bonding. And so that would be only certain examples. The compounds from this question here that have the ability to form hydrogen bonds to other molecules that do contain OH or NH in them, the bonds, would have to be the alcohol or the amine only in this case. Now, so which of the molecules can form hydrogen bonds with water? That means that the molecule doesn't have to have the OH or NH because the water provides the OH, because water is good old hydrogen hydroxide when you think about it. It's not too hard to figure out. But then it can be attracted to a lone pair of electrons on oxygen, nitrogen, or fluorine on another molecule. Well, so which ones of these compounds at the top here can do that? Not the alkane, it's still nonpolar, but the alcohol can still do it, so it's going to be the alcohol, and it's going to be, I'm going to mark these with a star, that's what I'm going to do. It's going to be this alcohol, and it's going to be the amine, because those already have hydrogen bonding opportunities. But the ether has a lone pair of electrons on oxygen, so it can hydrogen bond with water, and the ketone can too. So all of those choices are going to be able to hydrogen bond to water, and that allows some solubilities. The solubility will be discussed in Chapter 9 in more detail. Apologies for the technical clumsiness. All right, so hopefully you will take a look at the exercises to define intermolecular forces, which are those between molecules. And there are different types of them, but they're always between molecules. And those are three different types, depending upon what the components of the molecules are. There's going to be hydrogen bonding, which is only an intermolecular force. It fools people by its name, but it's only an intermolecular force. There's also dipole-dipole, which we haven't gone into in greater detail yet, but we'll hear a little bit more about it as we go on. And dipole-dipole only occurs in polar molecules. And the third one, I'm going to write by an abbreviation here, is called London forces. And London forces, London dispersion forces, are in any molecule. Anything with electrons will have London forces. What happens to intermolecular forces when a liquid is heated? These forces are disrupted. So they are going to be broken apart, and so hopefully that's when a molecule gets warmer, that's how come it can eventually turn to a gas. The intermolecular forces are disrupted and decreased until the point when it actually becomes a gas. So hopefully you've gotten some idea about the types of magnitudes, the strengths of intermolecular forces, what kinds of molecules exhibit hydrogen bonding, and predicting what relative water solubilities for a set of molecules based on the types of intermolecular forces that the molecules will have. Now, here's a little bit more information on intermolecular forces from the textbook that are worth your conversation, worth your knowing about. Gases have intermolecular forces that are negligible. That's what we understand for ideal gases. So molecules are so far apart that they essentially have none. In liquids and solids, the stronger the intermolecular forces, the higher the melting and boiling points. And this is the key thing to know about intermolecular forces. It allows us to predict or explain the melting and boiling points of various compounds and why they're similar or different. Those three types of forces we already have described, and they're shown here for their strengths, and the hydrogen bond is the greatest. You can see that the strength of the dipole and London dispersion forces overlap somewhat. It depends upon the size of the molecule, how strong the London dispersion forces are. Sometimes I'll note them as LF because that's London dispersion force. It's easier than writing it out. All right, so this is an example from the previous activity, Chem Activity 26, a reminder that you need to be looking at these exercises to be sure you know how to do these kinds of problems. And, whoops, go back. There we go. To be able to do these kinds of exercises and know how to set them up. This is one of the ones you should be looking at. It's always, the answers are posted on Blackboard. The question here asks us how to determine the partial pressure of oxygen, partial pressure of helium, and the total pressure. But I think I will leave this for another discussion since we don't really, that's not in the topic of the one I'm working on today. What I want to spend more time with instead is talking about the properties of liquids. Liquids have molecules that are in constant motion. They're moving around regularly in the liquid state. If a molecule has enough energy, it escapes to the gas phase, such as these little purple spheres are shown here. It breaks free of the intermolecular forces of the liquid and escapes to the gas state, and then we call it a vapor. So the vapor is the part that is the molecules that have escaped the liquid above the in the space above the liquid. If you put a device on here, this is called a manometer, you can measure the amount of pressure that that gas has if the container is closed. Notice there is a lid here. And there will be a vapor pressure when the system is at equilibrium for a particular temperature, and you can measure it with a manometer. That vapor pressure is something important to notice because it has some consequence elsewhere. It's the partial pressure of vapor molecules in the air above a liquid in equilibrium with the liquid. And so there's a vapor pressure movie on Blackboard, or it's also on Mastering Chemistry that you can look at that gives you an idea about how vapor pressure works a little bit. But if you don't watch it, that's okay too. So there's always going to be some pressure exerted by gas molecules in the vapor phase above the liquid, and you can measure it with that kind of device. So the vapor pressure movie shows you the vapor pressure of the vapors of bromine above the bromine liquid. Bromine liquid has got a high vapor pressure. In other words, a lot of the molecules escape to the gas phase readily, and it's a very colorful liquid, and the gas is likewise also colorful. Now, the consequence of vapor pressure is this, what you need to realize about it. The vapor pressure depends on what the liquid is and its identity and what temperature you're at. So it depends on the intermolecular forces, what attractions there are, and how many molecules can escape to the gas phase. The higher the temperature, the more the vapor pressure. So the more you heat it up, the more molecules escape to the gas phase, and that's represented for three different substances in this chart. The one that has the red curve is ether, which is also known as dimethyl ether, and that's in our Chem Activity 27. Dimethyl ether is shown to have a boiling point of 30. Oh, this is diethyl ether. I said the wrong one. Diethyl ether has a boiling point of about 35. See that on page 131 in your POGO book. You can reference it there if you can recall seeing that. And then there's ethyl alcohol, also known as ethanol, on the same page. Its boiling point is about 78. And then there's good old H2O water. And the reason you have three different curves is because there's three different substances and three different types of intermolecular forces. So if you look at the ether, if you recall what we described on Chem Activity 27, this molecule is not very polar. It's very weakly polar. It can hydrogen bond to water. That was something at the end of Activity 27, but it's essentially nonpolar. The more the polarity, the greater the intermolecular forces. So this one has weaker intermolecular forces. And so I'll make that note here. Weakest, at least on this chart, weakest intermolecular forces. Now, the other two, water and ethanol, have something completely different. And so what's up with these? Well, ethyl alcohol has a curve that's to the right here in the green, and ethyl alcohol has a structure that has CH3 on one end, and then it has a CH2 next to it. And if you looked at your Chem Activity 27, you might have come across this drawing as we were talking about it in class. And it has an OH group on the end. There you go, OH. That means there's your clue. That's what allows for hydrogen bonding. Water, of course, has the same thing. It has another OH group that, if I draw the geometry correctly, looks like a tetrahedral angle and allows for hydrogen bonds. So each of those two has stronger intermolecular forces, and they have higher vapor pressure for any particular temperature. So let's just pick a number, 80 degrees Celsius. Just pick one. 80 degrees Celsius, water has a vapor pressure that's about, looks like somewhere in the above 300 level, somewhere in there, and 300 millimeters of mercury. It's a pressure unit again. And ethanol, the ethanol at 80 degrees has a vapor pressure that's somewhere else. Oh my goodness, it's much way up here. So look way up here at the top. It's going to be somewhere over 800. Wow. Well, somewhere in there. So approximately or above 800 millimeters of mercury. And can you even find a value for the ether? Nope, you can't, because it's going to have a very, very high vapor pressure. It's way beyond this. So the vapor pressure rises with increasing temperature, but the difference of the liquids gives you different kinds of vapor pressures. So when the vapor pressure is equal to the atmospheric pressure, that's a definition of a normal boiling point, which is what's represented here. So the normal boiling points of each of these liquids is shown for the temperature at which the vapor pressure equals normal atmospheric pressure, which is 760, you get the boiling point. So ether has a boiling point here at 35-ish, ethyl alcohol is about 78, and water is 100. So the normal boiling point is the point at which the pressure is exactly 1 atmosphere, and it is going to be higher when the intermolecular forces are greater. Higher with greater intermolecular forces. That's a good point to remember. The greater the intermolecular forces, the higher the boiling point. So the vapor pressure and the boiling point of a liquid depend on those intermolecular forces between those liquid molecules. And if the atmospheric pressure is less than normal atmospheric pressure, such as at high altitude, if you go up in the mountains, the boiling points are lower as well. So think about water. If anyone's ever been camping up in the mountains, you know something about cooking is a little bit different. So if you say the atmospheric pressure is somewhat less than 1 atmosphere because you're up at high altitude, that means the boiling temperature of water is somewhere less than 100, so maybe it's 95. And that means that your water is boiling to cook your macaroni for your campfire dinner, and so it's going to take longer to cook it because it's cooking at a lower temperature. All right, the other properties of liquids that are influenced by intermolecular forces are these nifty things called surface tension and viscosity. Surface tension is what allows bugs to walk on water. All right, so enough of those things for today. And I hope that you find it is helpful to have gone through this discussion. Please ask questions as needed. Good luck with your homework.